All right, so we are going to continue on right where we left off. And we were just defined what a function was. We're now, even though I said the first thing that we want to do is look at the domain of the function. But before we even do that, let's talk about some notation. Let's talk about what is called function notation. So, function notation. And the idea here is the relationship between x and y is given a name, right? So when x and y have a relationship, instead of putting the y down, we actually give that relationship a name, right? So let's give it the name such as f. We only use function notation when the relationship between x and y is a function. The x is still used as the independent variable. But the y is actually replaced with an f of x. So y is replaced by this. And in this case, we use f, but there's nothing magic about f. It could be g of x or q of x or whatever of x. But the y is replaced by this function notation. And this is read f of x. Because we know that y is a function of that variable x. So we do that so that it makes it easy to plug things in. And as we work with function notation, we will see that when you plug things in, you just replace that x with whatever number it is that you want to plug in. So that is called function notation. And so where you might have seen y equals 3x squared plus 2x, instead of seeing that, you would see f of x equals 3x squared plus 2x. By using function notation, I can plug anything I want in for x without adding a whole lot of explanation. In other words, if I put in f of 2, then that would be 3 times 2 squared plus 2 times 2. And then I just calculate that out. 2 times 2 is 4 times 3 plus 2 times 2 is 4. So that gives us 16. Now, what that tells us is that the point 2, 16 is on this function. Because when I plug in 2, I get out 16. So I still relate that to an x and a y value, but this is the x, this is the f of x. So when I plug in x, I get out 16. So I could write that same ordered pair as f of 2 equals 16. And those two things mean the same basic thing. I can also plug in a variable if I wanted. So if I had that f of x, instead of putting in x, I could put f of x plus 2. Well, if f of x equals 3x squared plus 2x, and actually let me color code that a little bit better. So if I wanted to plug in something else, so let's say f of, and I'm going to plug in x plus 2 instead of x. Well, I have f of x defined like this, so now everywhere that I have an x, instead of that x, I'm going to put x plus 2. So if f of x equals 3x squared plus 2x, then f of x plus 2 equals this. Now, if I wanted to actually figure out that function exactly, I could FOIL out or box out that x plus 2. And that would give me x plus 2 times x plus 2, which is x squared, 2x, 2x, 4. Combine my like terms, and that becomes x squared plus 4x plus 4. So this piece becomes x squared plus 4x plus 4 times that 3 plus 2 times x plus 2. Distribute 3x squared plus 12x plus 12 plus 2x plus 4. And my end function is 3x squared plus 14x plus 16. So that is functional notation. That is how it is used. We will work with that all the time in this class, so it should become second nature to you rather quickly. So as we were alluding to at the end of the last video, we are going to talk about the first thing when we're analyzing a function that we want to discuss is called the domain and the range. So the domain is the set of all input values. It is the set of all x's. And the range is the set of all y. So everything that you can put into the function is called the domain, and everything that you get out of the function is the range. We are going to talk a whole lot about domain right now, and we're going to talk about range a little bit, but we'll talk about range in terms of looking at a graph, and then later on in the course when we do inverse functions, we will look at the range again. So let's talk about domain, right? How do we find the domain of a function? Finding the domain of a function. So first off, assume, let's start with all real numbers. So we start saying, all right, we got all the possible numbers that we could have. We have all real numbers. We can plug anything in. Then you've got to ask yourself two questions. Do we have any variables in the denominator? Right? If the function has a denominator, denominators cannot equal 0. So whatever is in the denominator cannot equal 0. So we start with all real numbers, then we throw out denominators cannot equal 0, so throw out any x that would cause this. If you don't have any denominators, you don't even have to worry about that rule. Then, thirdly, we look at even indexed radicals, right? Anything under an even indexed radical, and I'll explain this a little bit better after I write it. Anything under an even indexed radical, and what in the heck does even indexed radical mean? I'll get to that in just a second. Must be greater than or equal to 0. So and that's all we're looking at. So we've got two things that we have to consider. Denominators cannot equal 0, so throw out anything that would cause this. Anything under an even indexed radical must be greater than or equal to 0. So what does that mean? First off, let's talk denominator. Now let's talk about what this means, even indexed radical. Okay? So I'm going to get rid of that. when you see this little house with a number in it, you call that a square root, right? And we are familiar with the idea, right? That is called a square root, and it means that what number times itself? So the square root of 9 is 3 because 3 times 3 equals 9. And we don't even have a listed index on that, but the index of a square root is 2. If you wanted any other size root, you'd have to put a number there. So the cube root of 8 is 2 because 2 times 2 times 2 equals 8. Now, if I look at the quarter root of something, so like the quarter root of 16 is 2 because 2 times 2 times 2 times 2 equals 16. So this little number that we see here is called the index. And notice if there's none listed, then the index is a 2, but we never actually write that. Well, even indexes in the real number system, we do not have even indexed roots of negative numbers. Negative 9 does not have a root. Let's say negative 16. All right, so the square root of negative 16. Well, in the real number system, there is no number multiplied by itself that gives you negative 16. You can say 4 times 4 is positive 16. Negative 4 times negative 4, well, that's also positive 16. So this, in the real number system, does not exist. That's what we say when we say you cannot have a negative inside of a radical, right? If you had a odd root, like the cube root of negative 8, well, negative 2 times negative 2 times negative 2, having 3 negatives, negative times negative makes positive, times negative again, that makes negative. So the odd root is okay. It is the even root that you have the problem with. So when we're talking about domain, what it says is you cannot have the... All right, we're going to look at some examples of this, but we're going to do it in the next video because YouTube only lets you have 15 minutes at a time. I'm at 12 and a half, and I don't want to run out in the middle of a problem. So see you in the next one.